In the last video, we derived an expression for the evolution of A, the size scale of the universe, for a very specific case, the Einstein de Sitter universe, where we assumed that K was equal to 0 and the energy density is dominated by matter. This time, we're going to consider what is called the multi-component universe. Multi-component universe. All right, so in this case, we consider that the total energy density is composed of matter, the energy density in radiation, and the cosmological constant. And the energy density of matter will scale as the energy density of matter today times A naught divided by A cubed. Let's make this a little more clear. The cosmological constant is just that, it's a constant. And the energy density due to radiation is the energy density today times A naught over A to the fourth. The critical energy density today is defined to be H naught squared times 3c squared divided by 8 pi g. And this gives us a definition for the critical density today, for example, for matter, which is equal to epsilon m0 divided by epsilon critical today. And now we're going to use these expressions of each component of the energy density, and we're going to plug this into Friedmann's equation. And so Friedmann's equation, once again, is A dot over A squared plus C squared K over A squared is equal to 8 pi G epsilon over 3C squared. And I can rewrite this. So A dot over A squared plus C squared times K over A squared is equal to H naught squared times omega matter today, and then x to the minus 3. X will be A over A0. I'll write that down in a second. Plus omega radiation 0, x to the minus 4 plus omega lambda 0. And once again, x is equal to A over A0. So this is the multi-component form of Friedmann's equation. And then what we're going to do is let's go ahead and move this this curvature term, the c squared k divided by a squared. Let's move that to the right-hand side. So rewriting, we have a dot over a squared is equal to h naught squared, and then times, instead of writing all this stuff out that's in the bracket, I'm just going to do this. All right, so that's meant to represent everything that's in that bracket. And now subtract c squared k over a squared. Now notice that we have an a squared here, but we don't have an a0. So what I'm going to do is I'm going to multiply by 1. So a naught squared over a naught squared. This doesn't change that term. But now we have a term which is a squared over a naught squared in this term. In other words, x to the minus 2. Also, notice that if there's no h naught term, or h naught squared term, and if there were, this last expression, we could just put it inside this bracket somehow. So I'm just going to multiply by 1 again. All right. And in doing so, we're going to be able to take this term and put it inside this bracket. And when we do that, we're going to define a kind of like an omega k0 term, which is equal to minus c squared times k divided by a0 squared and h0 squared. All right, and with this definition, we now have our final expression for the multicomponent Friedmann equation. So a dot over a squared is equal to, which is h squared, right? That's h squared, is equal to h naught squared, and then stuff in bracket. And so we have omega r0 times a0 over a to the fourth plus omega matter 0 times a0 over a cubed plus omega k0 times a0 over a squared, and then plus the cosmological constant term in the bracket there. So that is our multi-component Friedmann equation. All right, and once again, the goal is to find a solution for A as a function of time. And one would integrate that equation to get there. So we're going to end up with an equation which is dA by dt is equal to a h naught times the square root of the stuff in the bracket. And one would need to find a solution to that. There are a few cases in which the solution to this equation is analytic, but most of the time you need a numerical solution. So you will get practice in your homework, writing a code in whatever you prefer. We'll walk through how to do it in Python, but you'll be able to write a code that will give you a solution for A of t. All right. There's one other thing to be careful about when with the nomenclature and the Friedmann equation and things like that. In a previous lecture, we wrote down the Friedmann equation in this form: c squared times k over a squared h squared. And we noted that all of these terms that are squared here, they're positive, and the only thing here that can be negative or 0 is k. So k is +1, 0, or -1. So it's that k that determines the sign. And we said that this is equal to h squared times omega -1. And we noted that if k is a certain value, it means that omega has to be either equal to 1 always, or less than 1, or greater than 1. and we use the sign here. And what I want you to be careful about is be careful about the definition of omega. So in this case, where I just wrote down this equation, omega is equal to the energy density divided by the critical energy density, which is equal to omega matter plus omega radiation plus omega lambda. And so that's the energy density. So that's what this expression is. There is a tendency for sometimes for people to write omega is equal to omega matter plus omega radiation plus omega lambda plus omega k. So which of these is the definition for omega? And it depends upon context. It depends upon the person. You can define either one. And so note that this latter one, it includes this pseudo energy density that we've included, omega k, but it is not an energy density. It comes from the curvature term from the Friedmann equation. It's just a useful way to encapsulate all of the terms into one dimensionless parameter, omega. Or maybe you would rather make sure that omega is just the energy density in the universe. It does not include the curvature. You just have to be careful when you see this equation, the Friedmann equation and omega, just note, is the curvature, as in here, the curvature term is by itself, or as in over here, does it seem like we're adding all of these terms together, including the curvature term that looks something like an energy density? But once again, it's not an energy density. It's just a term. It's a curvature term. All right. And that's what we have for today. That's the multi-component universe.